Okay. Good morning, everyone. I want to welcome you to another theory of statistics class. I'm actually going to say this today. In the night, I'm going to post makeup. Like I said, it's going to be left open for 48 hours. By 11:59 p.m. on Sunday, of course, you're not gonna have access to the exam anymore. It's just a makeup exam. It's not compulsory. It's for those who actually want to improve on their grade. Okay, so we started function of random variable on I think on Wednesday, and of course we're gonna continue from that today. I'm gonna say this. What we're gonna be doing today is mathematical. It's highly mathematical. So I will advise that you pay attention in case you need clarification. Please let me know. Okay, so today we're going to focus on method of transformations. I remember yesterday, on Wednesday, the focus was actually on the method of distribution function and the method of moment generating function. Let me have a quick recap, so that you'll be able to reconnect to this. Actually, we're working on a function of random variable situation where we know the distribution of a x, of a random variable s, and we define a new variable y, and that y is a function of s. And the question is, can we figure how the probability distribution of y? We know the probability distribution of x, but we define a new variable y that is a function of x. Can we also define, a probability distribution for a new variable y that is a function of s? Okay, and that is what we mean by function of random variable. So to be able to do that, we have identified three methods. Any of that can be used. We have the method of distribution function. I walk you through that on Wednesday. We also have the method of moment generating function. I walk you through that on Wednesday as well. So what is new today, okay, is the method of transformations. So this particular method is very, very crucial in statistical theory. So how we advise that you actually pay attention. Okay, so I want to welcome you into method of transformation. Okay, the method of transformation, like I said, just like any other method, like the method of distribution function, the method of moment generating function, of course, we can actually use this to figure out the probability distribution of a new random variable y, okay, where y is a function of s, and of course we know the probability distribution for x. Now, what I want to do, I want to apply this to discrete case. I also want to apply it to continuous case. And not only that, I'm going to apply it to situation where we got two variables and situation where we got one variable. Now let's get started. If you take a look at what I'm trying to showcase right now, okay, before writing on the board, I'm going to do this first. Okay, so if I have a discrete random variable s, okay, and of course, because it's a discrete random variable s, it's going to have a function of s, which is this is a probability mass function for that. Now, if we define y, and y is a function of s, okay, which we call the one-to-one transformation between the values of x and y, can we have a way to figure out the distribution of y? Okay, now to figure out distribution of y, using the method of transformation, what we're going to do, if we are working with discrete case, we need to solve for x. I'm going to say that again. If you're given y as a function of x, then I will solve for x. And after solving for x, then wherever I see x in the function, I'm actually going to plug in this particular guy. I'm done for discrete. And I want to walk you through an example on how that is going to work. Like I said, pay attention to this so that in case you need clarification, I'm actually going to explain that. Now, let's take a look at this example. Let x be a geometric random variable with probability distribution this. This is a geometric distribution. We've done this before. Okay, we use geometric distribution to model, event, where we actually want to figure out how many trials am I going to have before recording false sources. Of course, so this is a discrete probability type of distribution. Now, the question now is, if I know f of s, if I know the probability distribution of s to be this, and I've defined a new variable y, equal to s squared. Now, the question now is, we want to figure out the distribution of y. We know the distribution of x, but y is a function of x, okay? So, and y here is equal to s squared. If the distribution of s, what I'm trying to talk about, if the distribution of s is geometric, is the distribution of s squared geometric as well? That's what we want to figure out. Distribution of s is different from distribution of s squared, because the s squared here is actually y. Now, how do we go about this? Using the method of transformation. Do you know what I'm giving you now? I can also use the method of distribution function. Some of you can try that. We did the method of distribution function on Wednesday. You're still going to have the same result. But my focus today is, let me walk you through the method of transformation. Now, if I have y equal to s squared, if I want to use method of transformation, I will solve for x. When I solve for s, can you see what I got? If y equal to s squared, what it says, s equal to square root of y. Okay? Now, if s equal to square root of y, let me tell you this. Mathematically speaking, if I have s squared equal to y, I should have plus or minus. I think you know that. But because this is discrete, we do not want a negative. And that was why you see here, I just say s equal square root of y. Now, what am I going to do next? Wherever I see x here, wherever I see x in the conventional function given, I'm going to plug in square root of y. And when I plug in square root of y, this is what I'm going to get. Okay, when I get this, I need to redetermine the state space. Because 1, 2, 3, and so on like that here is a state space for random variable s here. I also need to define a state space for random variable y. And let me tell you this, I can make use of this. Y equal to s squared, right? So, which means when I square, if I want to get the state space for y, I need to be squaring this guy. What is 1 squared? 1. What is 2 squared? 4. What is 3 squared? 9. I'm done. Is there any question? To use the method of transformation with a discrete type random variable is very, very. I'm actually going to call that an easy peasy, because all what you just need to do is solve for s, and when you solve for s, then plug in the expression for s in terms of y into the function of s, and redetermine the state space. Okay, and I'm done. Okay, so this is the distribution now. Imagine if somebody asks you to find what is the expected value of y, then I'm going to make use of this distribution to figure it out. What is the variance of y? I'm going to make use of this distribution now to figure it out. Now, that is how discrete, how to implement transformation with a discrete random variable. But you know what? If I'm still working with discrete, but the function that I have is a function of x1 and s1, x2. x1 is discrete, s2 is discrete. The one I show you initially, we're only focusing on one variable at a time. Whatever the situation where I got two variables at a time, initially I have f of x1, s2. Of course, in this class, I've walked it through the joint, right? The joint distribution. Now, situation where I know the joint distribution of x1 and x2, and I want to define a new variable, y1 and y2, where y1 depends on x1, x2, and y2 depend on x1, x2. Okay? And the question now is, we want to figure out the probability distribution of y1, or the probability distribution of y2. Okay? So what are we going to do in that regard? Let me tell you this. Well, what we're going to do, because if I'm giving y1 as a function of x1, s2, y2 as a function of x1, s2, I'm still going to find the inverse. I'm going to solve for x1. I'm going to solve for x2. The other time, I only solve for x. But right now, okay, since two variables are involved, I'm going to solve for x1. I'm also going to solve for s2. So I'm assuming this s1. When I solve for x1, s1 is going to be a function of y1, y2. When I solve for x2, s2 also going to be a function of y1, y2. And all what I'm going to do, if I want to obtain the joint or distribution of new variable y1 and y2, all what I'm just going to do is to plug in x1 and the expression for x1 and the expression for x2 into the conventional probability joint function of s1 and s2. That is going to give me this. Okay? That's going to give me that. I want us to apply that now. And I need you to pay attention. We want to apply this now. Okay? Please pay attention. Let x1 and x2 be two independent random variable having Poisson distribution with parameter mu1 and mu2 respectively. Find the distribution of random variable y1 equal x1 plus x2. Please, I need you to pay attention. I actually here, do you know you have x1 and x2 that follow Poisson distribution, but they wanted to figure out what is the distribution of y1, where y1 depends on x1 and x2. Do you know here I can use the method of moment generating function? I can also use transformation. But you know what I want to show you now? I first want to show you the method of distribution, the method of transformation. And after that, I'm going to show you the method of moment generating function with this. Let's get started. Please, I need you to focus on the board. Okay, I need you to focus on the board. I need you to focus on the board. Okay, now, let us read the question. We're told here that x1 follow Poisson distribution with parameter mu1. x1 follow Poisson with parameter mu1. Obviously, the probability of, that x1 that we are talking about, okay, the probability of x1 that we are talking about is actually going to be this, mu1 raised to power x1 over x1 factorial. Of course, we've done, Poisson distribution, okay? So I'm actually going to have this guy to be that. Now, x2 follow poi with parameter mu2, okay? The probability of x2 is actually going to be this mu2 raised to power x2 divided by s2 factorial. You know, here x1 starts from 0, 1, 2 to infinity. Here s2 starts from 0, 1, 2 to infinity. Now, I need you to pay attention to what I just wrote right now. This is for x1, this is for x2. They have different mu. This has a mu1, this has a mu2. Now, we are told again in the question that the two independent random variables, they are independent. They are independent. Okay? Now, the independent actually mean the joint is just going to be the product of this guy here. Okay? We're told that they are independent. Okay? Now, in this class, we talk about independent actually means I should multiply the respective, I'm going to multiply this by this guy. So, and now multiplying that, I'm actually, I'm having this raised to power x1 divided by s1 factorial, this raised to power this, mu 2 raised to power x2 divided by s2 factorial. I multiply them together because, why? Why? Because I need this. Whenever I'm working with two variables, let me say this. Whenever we're working with two variables, we need a joint. We need a joint distribution. It's either you are giving the joint distribution, or if you are not giving the joint distribution, okay, and they give you the marginal distribution, this is a marginal distribution, and you have an information that x1 and s2 are independent, okay, if x1 and s2 are independent, okay, then for you to get the joint, you multiply the marginal distributions. Now, that's what I've done now. Now, in multiplying, and that's exactly what you see here. That's what you see here. But you know what? In multiplying this now, I want to simplify. Okay, in simplification, this and this can come together. I can just write one of that and put mu1 plus mu2. Okay, and mu1 raised to power x1, mu2 raised to power x2, divided by s1 factorial, s2 factorial. If there's somebody who doesn't understand this, ask question now. You know what I've just done? I just apply algebraic simplification. And that's why you have to give kudos to your teachers in elementary school, middle school, and high school for teaching you algebra. Okay? You're going to be making use of them now. Okay? Now, this is where we have. This is the joint. This is the joint. Now, the question is asking us, if you take a look at here, it says find the distribution of the random variable y1, find the distribution y1 equal x1 plus x2. Now, let me tell you this. We want to find the distribution of y1. And y1 is a function of x1 and s2. But let me tell you this. We cannot go from two variables to one variable. Please pay attention. We cannot go from two variables to one variable. If I were to use method of transformation, we can't go from two variables to one. You know what you need to do? You will artificially create another variable, which I'm going to say y2, and I'm going to say that equal to maybe any of this. That equal to, maybe I'm going to say y2 equal to s2. But let me tell you this. When I introduce this guy, okay, I'm actually going to factor it out in the end. It's just like maybe they invite me, maybe they invite me to a party and they said it's only couple that can come. Does that make sense? If they say, this party is for couple and my wife is not around, okay, I can just say, okay, my first daughter should follow me to the party. Okay, my first daughter is going to be graduating next year in college. Okay, I can ask her, follow me to the party. Okay, so that they will allow me to come in. But after leaving the party, what am I going to do to my wife, my daughter? My daughter is not my wife. I say, thank you. You represent my wife. Okay, my wife is back. Thank you. So what have I done? What I'm going to do is to factor her out. So what I'm trying to say here, I can't go from two variables to one. I will artificially create y2. So that when I artificially create y2, then what am I going to do? Okay, I need the inverse. I need to solve for S2. What is S2 here? Y2. What here I need to solve for X1. I need to solve for X1. Go ahead.
Is there a rule of creating the artificial variable?
That's a very good question. Let me tell you this. Because whatever you think of the artificial variable, okay, we can factor it out. There's no special rule that this should be artificial variable. But make sure your artificial variable is not complicated. Like for instance now, I have this plus this, right? Y1 equal to that plus that. Okay, the reasonable artificial variable that will be created is to say Y2 equal to any of this. Does that make sense? So, but in the end, whatever variable you create, whether simple or complicated, we can factor it out. But if you settle for complicated one, you may face a rigorous mathematics to be able to factor it out. And that's why we prefer to go for simpler one. But whenever a question like this come up, where you are adding, your artificial variable should always be equal to one of that. Does that make sense?
Then if there are 3 variables,
I would never go there for this class. I understand what you mean. That would be for advanced statistics classes too. We do Jacobian transformation for more than 3 variables. That's a multivariable situation. That would be beyond the scope of this class. That's a good question. Okay, now I've solved for S2, right? I need to solve for X1, right? If I want to solve for X1, it's going to be Y1 minus, look at this. If I want to solve for this, Y1 minus S2. But I'm not going to write S2. What is S2? Y2. Can you see that? What has happened now? What has happened now, I've been able to express X1 in terms of Y1, Y2, and S2 in terms of Y1, Y2. There's a Y1 here. Do you know there's a Y1 here? Okay? There's a Y1 here just like it's like this. You understand what I mean? So it's not showing because Y1 here is raised to the power 0. So what and that was exactly what we were talking about. Let me show you. That was what I was talking about here. Take a look at this. You're given this. And when you have this, you solve for what? You solve for X1. X1 will be in terms of Y1, Y2. And S2 will be in terms of Y1, Y2. That's exactly what we've done. And after doing that, what is it?